Hi everyone, my name is Shun and I'm here to present the achievements of our group project on Sberbank Russian housing market for CZ4041 machine learning. My team consists of Kyan, Isaac, Alvin, Jen, and myself, Shun. During this presentation, we'll give you a brief overview of our project's background and motivation. We'll outline the problem we aimed to solve and describe our methodology. We'll present our findings from our analysis and discuss their implications. We'll also highlight some of the challenges we faced during the project. Finally, we'll summarize our key takeaways based on our findings. To begin, we chose Sberbank Russian housing market because it piqued our interest. The housing market poses a great influence to our economy as well as the nation's well-being. The Sberbank Russian housing market dataset on Kaggle was used as it includes information such as their location, features, and price, which is useful when implementing a machine learning model that can reliably perform data analysis to accurately predict its prices on home and apartment values in Russia. Despite having existing algorithms that forecast real estate values, they frequently depend on a restricted collection of parameters that may not fully represent the complexity of the housing market. Hence, our problem statement is to create a model that uses a diverse range of features to accurately estimate the real estate values in Russia. Next, our methodology. Exploratory data analysis is a critical step to explore and analyze the data to gain insights and understanding of the underlying patterns and relationships of the data. Bivariate analysis of price against all significant variables such as school distance, fitness center distance, floor of the building, and more was used in this project. One crucial analysis was price against sub-area, also known as the district name, where it can be seen that the district with the highest and lowest average price circled in red are Hamiltonki and Porcellini Klenowsko, respectively.
Furthermore, highly correlated features of coefficient greater than or equal to 0.25 were selected to use in this heat map to help analyze the correlations between the variables. From this section of the heat map, we can see that the number of higher education institutions against the number of sport facilities in specified meter zone are highly correlated, which makes sense because sport facilities are commonly found within education institutions' vicinity. On the other hand, the number of higher education institutions is lowly correlated to the distance to nuclear reactors, showing that nuclear reactors are not necessarily located near education institutions. To prepare the data for the random forest model, the train and test datasets are concatenated. Columns with a correlation coefficient with the target variable price of less than or equal to 0.05 and 0 variance are removed. Data anomalies were then corrected by replacing them with missing values, and some of the conditions for this replacement are floor equals to 0, max floor equals to 0, number of rooms equals to 0, and a few others. Any columns with greater than 50% of missing values were dropped. Median imputation was carried out for columns with less than 10% of missing values. For all other missing values, k nearest neighbors imputation was performed. As for XGBoost, we checked for skewed data, and in the presence of such data, a logarithmic function was used to account for the skewed data. Then we went on to explore the possibility of outliers and remove them if they exist. Lastly, we removed anomalies in a similar fashion to the random forest model to reduce the effect of such data on our prediction. However, the missing values are not replaced due to XGBoost support for missing data. For LGBM, what was done to clean the data was to remove the price outliers before the model is applied. By doing so, it reduces the tendency for the results to skew towards a certain way due to the presence of outliers that are priced beyond the trend. After completing these data preparation steps, the clean dataset is ready for each model to run on. We will then use the aforementioned models to predict the prices of residential properties in Russia based on various features, amenities, and other variables.
Before we talk about the evaluation of models,
The first model we have decided to evaluate is the Random Forest Machine Learning Model, or RF in short. What is the random forest? In general, it's a supervised machine learning algorithm that is widely used for the purpose of classification or regression. In our case, we will be using random forest for regression since housing prices are continuous. The random forest regressor is an ensemble learning technique for decision trees, since it creates multiple decision trees on random data samples and takes the average case. Random forest has some advantages over other models. The combination of multiple decision trees helps to reduce overfitting in decision trees and helps to improve the accuracy of the model. Random forest is also able to handle large number of input features well, which is useful for housing data since housing prices may be affected by many inputs such as size and location. Next, random forest is able to automate missing values, which is common in real-world housing data. Random forest is also robust to outliers, which is essential when evaluating housing data, as they often have outliers due to the unique characteristics of properties. Finally, random forest can handle the non-linear relationships between the input features that affect housing prices. Random forest can do this by allowing each decision tree to capture a different aspect of the relationship and then combining the trees to make a final prediction. Next, we have 3 steps to improve the performance of the model. The first is converting categorical data into numerical data. The motivation behind this is because decision trees generally handle numerical data much better than categorical ones. For this conversion, we have utilized Python's built-in label encoder function. Next, transformation of feature matrices is done to reduce its dimensionality to identify the features that capture the most important data characteristics. This helps to improve the model's performance. Finally, hyperparameter tuning is an important aspect of machine learning because it helps to generate optimized hyperparameters that maximizes the accuracy of the model. The hyperparameters will be tuned with the number of estimators and max depth of the decision trees. For this purpose, we utilize a function in the scikit library called randomized search CV.
The next model is called Extreme Gradient Boosting, shortened to XGBoost. XGBoost is a powerful algorithm building onto the normal gradient boosting algorithm that builds decision trees in parallels rather than in sequence. It utilizes classification and regression trees to store real-valued scores in leaf nodes. The scores can be converted later into categories to support classification problems or kept as is to solve regression problems. XGBoost focuses on high computation speeds for large data sets while still providing high model performance for classification and regression problems. It also can learn how to support missing data by minimizing the loss function. XGBoost models are generalized due to advanced regularization and can support the combination of categorical and numerical features within the data. All these features prove useful to be applied to our dataset. In order to prevent overfitting, there is the need to tune the hyperparameters of the model. We tackle the tuning of 5 different parameters in our experimentation: max depth, minimum child weight, subsample, constant sample by tree, and ETA, which is the learning rate of the model. We use grid search to test different combinations of hyperparameter values and use cross-validation to compare the average mean absolute error of each combination across the validation folds. Looking for the minimum MAE gives us the best performing model with the specific parameter combination after the cross-validation process. We then look for the smallest MAE across the combinations of parameter values. This cross-validation process, however, provided so-called best values that seem to make the model overfit, and hence the values were tweaked to make the model simpler. The XGBoost model is trained using the tweaked hyperparameter values for a maximum of 1000 boosting rounds. An early stopping value of 20 is set such that if the RMSE of the model on the validation set does not decrease after 20 consecutive rounds, training will come to a stop. The iteration with the best RMSE score is taken as the point to stop. The model is then trained again, starting from the best RMSE score round recorded from the early stopping procedure. The model is then used to predict the test data and produce the final CSV file.
The final model we have decided to evaluate is a light gradient boosted machine regression model, or as it is known as light GBM. It uses decision trees to improve the accuracy of models used for ranking, classification, and other tasks. One of the unique features of light GBM is that it splits the decision trees leafwise rather than depthwise like other boosting algorithms. By splitting the tree leafwise, light GBM is able to reduce more loss and improve accuracy to a degree that's difficult to achieve with other boosting algorithms like XGBoost. This makes light GBM a faster, distributed, and high-performance gradient boosting framework that can be more well-suited for the task that we are working on. What makes light GBM better is due to it utilizing two innovative techniques: gradient-based one-side sampling (GAUS) and exclusive feature bundling (EFB). GAUS retains instances with larger gradients and performs random sampling on instances with smaller gradients. This allows light GBM to take advantage of the fact that data instances with larger gradients contribute more to information gain than those with smaller gradients. EFB is a method of reducing the number of features without losing too much information. It bundles together features that rarely takes non-zero values simultaneously in this sparse space, creating an exclusive feature bundle. This improves efficiency while maintaining accuracy. Similar to XGBoost, we are also required to ensure hyperparameters are adjusted to prevent overfitting. These requirements will be having a small learning rate but increase the number of iterations to account for the smaller step size. The tree depth will also have to be kept while keeping the number of leaves sizable. For this model, we have utilized bagging to randomly sample the training data without replacement. This is done in order to reduce overfitting and improve the generalization ability of our model. We also reduced training time by randomly selecting 70% of the features whenever a new tree was constructed. As mentioned previously, the numbers here are the chosen hyperparameters based on the requirements we have stated in the previous slide. The model is then trained to be used for predicting the test data and produce a final CSV file.
Next, I'll share more about the results and discussion. The CSV file consisting of the prediction results for each model was submitted on Kaggle public and private leaderboards to identify the ranking position, with light GBM achieving the best result. Our output submission file based on light GBM achieved a score of 0.31 as shown above. When we compared our score to the public leaderboard, we are ranked 610, and as for our private one, we have gotten an impressive rank of 57. Next, I'll share more about our discussion. From the results shown previously, light GBM has the best performance. This is because it finds the ideal split points using a histogram-based approach, allowing it to analyze big data sets significantly quicker than other algorithms. Furthermore, its gradient-based one-side sampling in handling categorical variables helps to reduce the number of categories by sampling only the crucial ones. To add on, its exclusive feature bundling technique for regularization helps to prevent overfitting of the model. As such, light GBM is a powerful algorithm that combines speed, efficiency, and accuracy, which outperformed XGBoost and random forest.
For the challenges, with any large dataset, it is essential to perform proper pre-processing of the data and feature engineering. Without proper understanding of the datasets, meaning removing data points that seem to be an outlier, could lead to an improper training dataset for the model to learn. As such, variables with low correlation coefficient or containing data anomalies were removed. To add on, preparing data for each model must be carried out independently, considering the distinctive requirements of each model. Starting with random forest, its extreme data anomalies were removed based on the conditions set by us to reduce its effect on our prediction. Secondly, XGBoost further requires a logarithmic function to account for skewed data to be removed. Lastly, light GBM requires any remaining price outliers to be removed before the model can be applied. In conclusion, 3 different algorithms were experimented in this project, namely random forest, XGBoost, and light GBM, on the Sberbank Russian housing market dataset, and all of them performed well on this dataset. Random forest provided a good accuracy on this dataset, but it took a longer time to train compared to XGBoost and light GBM. They both provided higher accuracy, with light GBM slightly outperforming XGBoost, making it more suitable for real-world applications. Lastly, the importance of feature engineering helps to achieve better accuracy in machine learning models by removing outliers. Overall, these 3 algorithms are powerful tools in machine learning and can provide valuable insights in the real estate market. The choice of algorithm would depend on the specific requirements of the task, such as accuracy, training time, and the size of the dataset. By using machine learning models to estimate real estate values, it is possible to improve the efficiency and transparency of the market, where we are able to make more informed decisions about the housing market. With that, we have come to the end of our presentation. Thank you so much for your kind attention.